Hello everyone, this is Sid from Sony. In this video, I will be sharing in-depth details of a paper titled HyperReenact, One-Shot Reenactment via Jointly Learning to Refine and Retarget Faces, which was presented at ICCV 2023. In this paper, the authors present a method for neural face reenactment called HyperReenact that aims to generate realistic talking head images of a source identity driven by a target facial pose. The theme revolves around the task of facial reenactment, that is, facial expression transfer under one-shot setting. Summarizing the two key contributions of the paper. First, HyperReenact is one of the first works to show the effectiveness of merging the steps of inversion refinement and facial pose editing for achieving robust and realistic face reenactment. Authors propose a novel framework that leverages the adaptive nature of hypernetworks to alter the weights of a powerful style GAN to perform both refinement of the source identity and reenactment of source face in the target facial pose. Second, hyper-reenactment exhibits robustness to large head pose shifts and challenging cases where the source face is partially self-occluded, primarily by leveraging the generation and disentangled properties of a pre-trained style GAN2 generator. More about the theme of this paper. The task of face reenactment involves generating photorealistic portrait images of a still source person given the expressions of a target person. Such algorithms target key facial regions to render, such as face, hair, neck, shoulder, and further fine-grained regions like lips, teeth, pupils, etc. Briefly covering the related works, these fall across three categories. First is facial image editing. These methods leverage the remarkable ability of modern pre-trained GANs like StyleGAN2 in producing photorealistic facial images to edit various facial attributes such as head pose, facial expressions, or hairstyles. The key idea is to manipulate the latent representations like W, W plus, or S codes of the generator to learn meaningful editings of different semantics on the synthetic images. Despite their effectiveness in editing synthetic images, such methods fail to manipulate real images with non-native or external latent code. Discussing one such method called style mask, which performs facial image editing by learning to disentangle the style codes of the source and the target images in the style space S of a pre-trained style guide 2. The source style code consists of individual's identity, and the target style code is comprised of head pose and facial expressions to be transferred. The final image is generated by passing reenacted style code through a generator. Next category is called real image inversion. GAN inversion methods allow for encoding of real images into the latent space of pre-trained generators, which allows for semantic image editing. Existing inversion methods mainly focus either on optimization-based approaches, which is computationally expensive, or on encoder-decoder based architectures. They struggle to faithfully reconstruct the real images by losing source identity characteristics and produce unwanted visual artifacts in the synthetic image. HyperReenact falls under this category and aims to tackle these challenges by using a hypernetwork to predict weight offsets through reenactment and GAN inversion. Hyperinverter is one such method which encodes the input image to a content code in W space of StyleGAN, and it extracts appearance code from fusion of input and target image pairs. Then it applies a series of hypernetworks to embed the appearance code to the generator for reconstructing the final image and recover the missing information during inversion. The final category is called neural face reenactment. Such works focus on learning disentangled representations for the identity and the facial pose using 2D priors like facial landmarks or 3D priors like 3D morphable models. Despite their realistic results in small pose variations, such methods fail in the more challenging and realistic conditions of large head pose variations and produce images with several unwanted artifacts. A state-of-the-art neural face enactment method called PI renderer maps the input motion descriptors consisting of 3DMM parameters to a latent space and generates a coarse image based on the motion estimated using warping network. Finally, the editing network generates the final image by editing the coarse result through image-to-image translation. Let's have a look at the overall architecture of HyperReenact. The network consists of two main stages, reenactment and generation. Given a source image IS and a target image IT, it first extracts source appearance features and the target pose features using a pair of encoders. The reenactment module learns to effectively fuse these features, producing a feature map FR that serves as input to each reenactment block of hypernetwork module H in the generation stage. The task of H is to predict offsets, delta theta, and update the weights of StyleGAN2 generator so that using the inverted latent code, WS generates a new image IR that conveys the identity characteristics of the source face and the facial pose of the target face. They use another encoder to perform GAN inversion, encoding source image IS to a style code WS. Let's discuss each of these modules in detail. In the first stage of reenactment, the framework extracts the corresponding appearance features FAP and facial pose features FP from source and target images, respectively. Then they use a reenactment module to produce a combined feature map FR such that the identity or appearance information is adopted from the person in the source image and the facial pose characteristics are based on the person in the target image. To encode the appearance of face, they use the popular ArcFace encoder. ArcFace is trained on face recognition tasks. As a result, its features only capture the identity characteristics of a face. Similarly, to encode the facial pose of a face, they use the encoder EP, which is a pre-trained 3D shape model called DECA. DECA is trained on 3D facial shape model reconstruction. Hence, the extracted features only capture the facial pose without taking into consideration the appearance. FAP of shape 512 by 7 by 7 is taken from the output of the last convolutional layer of ArcFace, and FP of shape 2048 by 7 by 7 is extracted from the last convolution layer of encoder EC, highlighted in the image. EC is based on ResNet 50 block with a couple of fully connected layers at the end. Reenactment module performs the crucial task of generating a feature map which combines the appearance features from the source image and the facial pose feature from the target image. It is inspired by SPADE module. As shown in the figure, the RM includes a 1 by 1 convolution to project FP into the same channel size as FAP. Then, after each feature map, it learns two modulation parameters, namely gamma and beta. The final combined feature map FR is calculated with the expression shown on the slide. The symbol denotes element-wise multiplication. In the next stage of generation, they first invert the source image IS into the W space of StyleGAN2, producing style code WS. A hypernetwork H is employed, which is learned to generate weight offsets using reenactment blocks and fused feature map FR. Then it updates the individual weights of StyleGAN2 generator across each controllable layer. Finally, StyleGAN2's generator produces synthetic reenacted image based on the style code WS and the updated weights. The generator of StyleGAN2 takes as input random latent codes sampled from standard Gaussian distribution, which are then fed to the mapping network to get the intermediate latent codes in the W space, or sometimes it's extended W plus space, where a different latent code is fed to each of the N layer of the generator. Using the W plus latent space for real image inversion results in better reconstruction quality by enhancing the expressiveness of the generator. In HyperReenact, they get an initial inverted latent code by using an off-the-shelf method called E4E, which inverts the real images into the W plus space, containing n different style codes of 512 dimensions each. The encoder EW outputs a single style code W together with a set of offsets delta 1 till delta n minus 1, where n denotes the number of StyleGAN's modulation layer. The final latent representation is obtained by replicating the W vector n times and adding each offset delta I to its corresponding entry. The hyper network module consists of M reenactment blocks, where M is the number of layers to be controlled, and N is the total number of layers in the generator. So M could be equal to N or less than N. Each RB takes as input the combined feature map FR and outputs an offset theta delta L of size Cout by Cin by 1 by 1. The offsets are then spatially repeated by the kernel dimension of each layer, that is KL by KL. This step is done to reduce the number of total learnable layers and parameters. Finally, the updated weights for each layer L of the generator are computed as shown in the slide. Diving one step deeper into the hypernetwork architecture, authors propose to use two of the reenactment blocks, namely shared reenactment block and layer-specific reenactment block. In both types of blocks, the input feature map FR is first fed into a series of convolutional layers that process and downsample the input into the shape of 512 by 1 by 1. In the shared reenactment blocks, the downsampled feature map is then flattened and fed into a fully connected layer. Afterwards, the two shared fully connected layers are used to calculate the output feature map of shape Cout by Cin by 1 by 1, which is repeated spatially so as to match the shape of the convolutional kernels Cout by Cin by KL by KL. In layer-specific reenactment blocks, after the series of downsampling convolutional layers, the computed feature map has a shape of 512 by 1 by 1. This feature map, upon being flattened, is fed into a final fully connected layer, which outputs a feature map of shape Cout by Cin by 1 by 1, and again it is spatially repeated to have a shape of Cout by Cin by KL by KL. HyperReenact's training process follows a curriculum learning scheme, where the complexity of the training data is gradually increased across three phases: a real image inversion, self-reenactment, and cross-subject reenactment. A key thing to note here is that only the weights of the reenactment module and the hypernetwork are updated during training, while inversion, appearance, and pose encoders, as well as StyleGuide2 generator, are kept frozen. On the first training phase, the source IS and target IT images are the same. Given the appearance and the facial pose, the input image as well as the initial inverted latent code W, the network is trained to refine the missing details between the real image and its initial reconstruction using W. The training objective uses the following losses: L1 pixel-wise loss, LP-IPS perceptual loss between the real and the refined image, identity loss by taking cosine distance of embeddings extracted using arcface, and gaze loss computed using L2 distance between gaze direction extracted using an off-the-shelf gaze estimation network. During the second training phase, the model is trained on self-reenactment, where the identity of the input source and target images is the same, but the facial pose is different. Given appearance of IS and facial pose of IT, the network is trained to predict offsets delta, theta, so that the reenacted image IR has the identity of the source and facial pose of the target image. The same loss functions are used as in phase 1, however, now computed between reenacted target image pairs. Additionally, they also use shape loss to transfer facial pose of target image, computed by taking L1 distance of the 3D facial shapes extracted using Deca. To further enhance the results on cross-subject reenactment, the model is fine-tuned on self-enactment using cross-subject image pairs in final phase 3. Since it is a challenging task, they concurrently perform training for the tasks of self and cross-subject reenactment to ease the training process by letting half of the image pairs in each batch to correspond to each task. The objective is defined the same as phase 2. However, shape loss is computed between source and reenacted image pairs, and gaze loss between target and reenacted image pairs. For training and reporting results on self and cross-subject reenactment, authors use VoxLF1 dataset, which contains over 15,000 videos extracted from YouTube. The face regions are cropped and resized to a resolution of 256 by 256. For quantitative evaluation, the following metrics are used. CSIM, Cosine Similarity Index, which measures the similarity of identity embeddings extracted using ArcFace model to evaluate the identity preservation capability. LPIPS, a Learned Perceptual Image Patch Similarity, evaluates reconstruction quality by computing similarity between activation maps of two image patches. FID, or Frechet Inception Distance, measures the closeness of distribution between real images and generated images using Inception V3 network layers to evaluate the realism of output. FVD, or Frechet Video Distance, is the same as FID, but it evaluates the temporal consistency of generated videos and takes an input as a video rather than an image. Finally, APD, average pose distance, and AED, average expression distance, is the L1 distance between pose and expression parameters, respectively, estimated using an off-the-shelf 3D face reconstruction model, DECA in this case. It evaluates the motion transfer capability of the network. They evaluate and compare their method against several existing state-of-the-art one-shot face reenactment methods outlined on this slide. The method offers a wide range of diversity in terms of internal mechanism of operation, ranging from 2D facial landmarks, 3D parameters to pose networks like Net3D. All these methods generate 2D images except one, ROM, which performs 3D aware generation based on flame. This slide shows qualitative comparisons on self and cross-subject reenactment. HyperReenact is able to produce mostly artifact-free images and faithfully transfer the target facial pose, including head orientation, facial expression, and gaze direction. The results are robust to the challenging task of cross-subject reenactment, even with extreme head pose differences. The table on the slide reports the results both on self and on cross-subject reenactment. In the task of self-reenactment, HyperReenact outperforms all the other techniques on CSIM, APD, and AED, showcasing its good reconstruction quality with accurate motion transfer capability. LPIPS, FID, and FVD metrics are comparable to the existing methods in terms of realistic looking image generation. In more challenging tasks of cross-subject reenactment, HyperReenact outperforms all other techniques on identity preservation with CSIM and head post transfer using APD, while being on par with Rome on expression transfer. Additionally, they also conduct a user study by presenting 20 randomly selected image pairs to 30 users and asking them to select the method that best reenacts the source frame, as denoted by the column user preference percent. Majority voted for their method to be the best in terms of facial post transfer and image quality. Here is a video comparison on the task of self-reenactment. Another video on cross-reenactment. Additional video results for both the tasks of self-reenactment as well as cross-reenactment. Finally, I would like to report the results of the ablation studies performed by the authors. Authors compare the reenactment results of the network trained with and without curriculum learning scheme. As shown in the table, the model trained without curriculum learning achieves poor results on head pose APD and expression transfer AED and identity preservation on self-ID reenactment. This is also shown in the figure where CL leads to less visual artifacts on reenacted images. However, the model trained without curriculum learning has some artifacts, especially around eye region. Second, authors compare their method with and without training on cross-subject data. As shown in the table, when fine-tuning with cross-subject data, quantitative results respect to identity preservation are improved, especially on cross-subject reenactment. This effect is also shown in the figure, where the identity leakage of target face into the reenacted face is reduced. Finally, they perform experiments with and without using the gaze loss and evaluate its contribution. Specifically, in the table, the gaze error is computed on real image inversion, self-reenacted, and cross-subject reenactment. Moreover, looking at the figure, we can observe that using the gaze loss improves the faithful reconstruction of the gaze direction of target images. Despite achieving competitive results in the task of one-shot face reenactment, there are some cases where hyper-reenactment fails to generate artifact-free images. In cases where the source facial images depict accessories such as hats or eyeglasses, it fails to reconstruct them in detail. For instance, in the first case, the reconstructed glasses are completely different than those in the real image. Similar trend is observed in the second and the final row for hats. Moreover, HyperReenact is not able to learn how to refine or reconstruct any details on the background of generated images, as observed in all of the three inverted images. Also, identity of the inverted image is sometimes completely changed, as observed in the second case, where the inverted image contains different facial shape and characteristics when compared to the real image. I will wrap up the video here. Thank you.